Dear students of B.Tech first year, I am Dr. Arvind Parsai, Associate Professor of Mathematics in Engineering Science Humanity Department at Chamni Devi Group of Institution Indore. I want to teach you through this video lecture 5 solution of differential equation of first order and higher degree by method 2, 3 and 4. So the second method is equation solver for y, that is we are having the problem in general form as first order and high degrees of f of capital F of x y p equal to 0. Then let the differential equation given by 2 by solvable for y, then y can be expressed as a function of x and p, that is from this equation 2.2 if you are able to separate y in terms of x and p, it means that this type of question is solved for this y. So that's why we write in this continuation this equation by 2.9. And then now the next step is you differentiate this type of equation by with respect to x on the both side. So this gives to you differentiation is del f upon del x plus del f upon del p into differential of p with respect to x is dp by dx. Then this equation 2.10 is a first order differential equation of first degree. Also in x and p it may solved by any one of the methods here. So let me assume that their solution is to be expressed as phi of x p c equal to 0. The solution of the equation 2.9 is obtained by netting p from 2.9 and 2.11, and if elimination of p is not possible, then 2.9 and 2.11 together may consider parametric equation of the solutions of equation 2.9 with p as a parameter. Let we understand this method by an example. So the given equation can be written as, it is clear that the given equation is solved for y, that is we can separate y in terms of the remaining variable as, so 1 plus p square under root of this. Now differentiate on the both side this equation number 2.12 with respect to x on the both side. So this gives to you, so first the differential of power here function is 1 by 2 of 1 upon 2 into under root of 1 plus p square. Then the differential of inner function is with respect to x is, first you differentiate power of this p as 0 plus 2 of p, then into differential of p with respect to x is dp by dx. Or this equation can be written as p equal to, because we know that dy by dx equal to p small p equal to 2 से 2 कट गया आपका p upon under root of 1 plus p square under root of 1 plus p square of dp by dx. Or you can write into separable forms, variable separable form here, or simply you write as in this pattern as by taking p as common, so 1 minus 1 upon under root of 1 plus p square of dp by dx equal to 0. Call it as equation number 2.13. So 2.13 for p equal to 0, this equal to 0, or 1 minus 1 upon root 1 plus p square of dp by dx equal to 0. So by solving p equal to 0 in 2.12, so we get y equal to 1. And by solving this 1 minus 1 upon under root of 1 plus p square of dp by dx equal to 0, and because we get a separable equation in p and x, this is you will get separable forms. So dp upon dx equal to under root of 1 plus p square. or we can write as dp upon root of 1 plus p square equal to dx, or we can write down integration of this. The integral of this is sine in hyperbolic inverse p equal to x plus c, or we can write as p equal to sine hyperbolic x plus c. So now here in this problem you are getting p, and so that's why you can eliminate p from 2.12 and 2.14. You obtain here y equal to cos hyperbolic x plus c, and y equal to 1 of the given equation is a singular solution, as it cannot be obtained by giving the particular value to c in equation number 2.15. So let me come to similarly the next method, that is method number 3 of solving this category of problem, which we called as x solver for equation solver for x. That is, if you are able to express x as a function of the remaining parameters here, that is y and p. So let the equation 2.2 be solvable for x, that is x equal to some function of y comma p. Then, as I argued in this previous section of for y, we get a function psi such that psi of y comma p comma c equal to 0. So by eliminating p from 2.16 and 2.17, we get a general solution of 2.2. If the elimination of p with the help of 2.16 and 2.17 is cumbersome, then this equation may be considered parametric equation of the solution of 2.16 with p as a parameter. So let me understand this method by an examples, or this method is well explained by an examples. Suppose this is a question of first order, clearly in high degree, that is degree is greater than 1. So our first option is to put dy by dx equal to p. Then this equation is to be written as xp cube minus 12p minus 8 equal to 0. Since in this equation only the power of x is 1, that's why of course this type of question is only solved for x easily here. So that is, it is solved for x, that is equation can be written as x as a function of remaining terms as 12p plus 8 upon p cube, that is 12 upon p square plus 8 upon p cube. Now you are differentiating both the side with respect to y by calling this equation as 2.18. So on differentiating with respect to y, this gives to you left side differentiation at dx upon dy, while right side terms differentiation is minus 12 upon 12 into 12 upon p cube of dp by dy minus 3 into 8 upon p4 into dp upon dy. So now by taking here, simplifying as here, so 1 upon p, because dy by dx equal to p, so the value is 1 upon p. So minus 24 upon p cube dp by dy, 8 3 24 upon p4 dp upon dy. Or we can write this equation into variable separable form here, and then on integrating this and both the side separately, this gives to you here the integration of the left side is y, integration of first term is minus p raised to minus 2 plus 1, and divide by this becomes plus 1, so 24 upon p, and this gives to you divide by 2, so 24 divided by 2, this gives to you 12 upon, and the power is making plus, so p square plus some constant of negation is c. Call it as equation 2.19. So the equation 2.18 and 2.19 constitute parametric equation of solution of the given differential equation, because we cannot find the value of p separately. That's why you write the equation x as a function of p and c, and y is also as a function of p and c. So this is about your method number 3. Now we come to the last method, as method number 4 is Clairaut's equations. So first we understand the method, then we come to an example. So we have the problem in this pattern here. Let the equation 2.2 be of the first degree in x and y, then this can be written as y equal to x of from function of p was phi1 of p plus phi2 of p. So equation 2.2 is known as Lagrange's equations. So that is y equal to px plus f of p, you can say that. So if phi1 of p equal to p, then the equation is y equal to px plus phi2 of p. So this is known as Clairaut's equation. Now since y can be expressed as a function of p and x, so which method is applicable? We have apply my equation solve for y. So this question is solve for y. So what you are doing when first order and high degree differential equation for solving y with respect to y, just by differentiating with respect to x. So on differentiating both the side with respect to x, by applying the product formula of differentiation, first function का differentiation आपका x आपका as it is means second function का differentiation, suppose it is phi1 of p plus x pi dash of this, and p का differentiation होगा dp by dx, and phi2 dash of p plus phi2 का होगा differentiation, p का x रेस्पेक्ट होगा dp by dx, and then this can be write as p minus phi1 of p equal to inside this bracket x of 5 dash of p plus phi2 of p dp by dx. From this we get here x plus phi2 dash of p of dp by dx equal to 0 for phi1 of p equal to p. So this gives to you dp by dx equal to 0, or we can say that x is some function phi2 dash of p equal to 0. So dp upon dx equal to 0, that is p equal to c. So by putting value of p equal to c in equation number 2.21, we get y equal to cx plus phi2 of c. So this is the general equation, general solution of the Clairaut's equation. Now we come to explain this method by these examples. So suppose this is an example. So of first order and degree 2. So just by putting p equal to dy by dx, then this equation can be written as p minus 1 y minus px equal to p. So this equation can be written as y equal to xp plus p upon p minus 1, that is now on differentiating with respect to x. So this gives to you after differentiation with respect to x, dp by dx of x minus 1 upon p minus 1 का whole square equal to 0. Thus either dp by dx equal to 0 or x minus 1 upon p minus 1 का whole square equal to 0. So dp by dx equal to 0. So this gives you after integration p equal to c, and since x of this is not to be 0, therefore on putting this value of c in the equation, we get y equal to cx plus c upon c minus 1, or y minus cx into c minus 1 equal to c, which is the required solution of the given problems by Clairaut's forms. Thank you very much.